Welcome. This is our setting you up for analysis presentation. So last week, Alex, Nate, and Anil gave us a presentation on what failure is and kind of like what failure modes are for your parts and why they're important, and then how to design a part with those failure modes in mind. So this week, building off of that, our purpose is to have you understand what the benefits of a finite element analysis model are, what their limitations are, and then how hopefully give you like the background to approach an analysis case with the right mindset. So we're not necessarily going to be going through and being like, these are the buttons you press, but more of like, here's how you think about all analysis or finite element analysis. So what is finite element analysis, or FEA? It is simply a way to predict how a given system or part behaves under certain conditions. You may be tempted to think about it as sort of a magic wand that you tap your part with and it makes it perfect. Unfortunately, this is not the case. There's a lot more that goes into it. You actually need to understand your solution space and the problem you were trying to solve pretty well before going to FEA. So based off of the past presentations, you've learned how to make your requirements and your constraints that then build a solution space that then use hand calcs to refine, which gives you a well thought out design, which then you put into analysis using the list of failure modes that you have determined as part of your hand calc work for this part. Just remember, junk in equals junk out. So you have to know what you're putting in to FEA for it to matter. So there are a few kind of like definitions we just want to go over really quick. Material selection, mesh, boundary conditions, which include fixtures and loads, and factor of safety. So material selection, the shape and material affects the analysis, which sounds really simple, but it actually makes a huge difference what material you have to put the correct material, and by correct I mean as close to reality as possible, into your program to get accurate results. And this even matters between different alloys of a material because it can have significant impact. And obviously don't put Legos when you need steel. The picture is a little misleading. So a mesh kind of describes what FEA is in general. FEA basically takes your super complicated geometry, it breaks it down into tiny pieces, then it solves partial differential equations for each of those tiny pieces, puts them back together, and then solves for how those pieces interact to the ones next to them in that larger part. So that's why it's called finite element analysis, because it breaks these things into little elements is what they are called. And so you might be like, okay, cool, like the smaller the element, the more like fine-tuned my analysis will be. But the more elements, like the more little pieces you have, it's gonna run, the runtime for your analysis is going to increase. So more elements is not always good. So another important thing are boundary conditions, and one of those is fixtures. In real life, your part is going to be held in place or constrained by fasteners or joinery or something like that. You need to represent these fixtures in your analysis, otherwise you're not going to get accurate results. A good example of this is kind of your standard cantilevered beam problem. And this is also a good example of making an assumption about your fixtures, because if you were to put this case into analysis, you would assume that the fixture between that beam and the wall is unbreakable, right? Like, because you want to see the deflection in the beam, so you're going to assume that that fixture is made with like the strongest glue ever, and you're not going to have to worry about it. So that's an example of an assumption in fixtures that will make your analysis easier. Another boundary condition is loads, which, using the same example, is then that force just at the end of the beam. So you use your hand calcs to determine what the loads are on your part. And in formula specifically, this does not happen in the real world. A lot of the times our loading conditions are determined by the rules. So that could be helpful. You want to make assumptions on how your part is loaded for any given scenario. There's going to be an almost infinite number of load cases that your part could potentially see, but you want to make an assumption like it is in this image, that there's one force. This is the most likely force we're going to see at the end of the beam. So factor of safety is also an important concept to think about when you're doing FEA. Factor of safety is basically how much stronger your system is than it needs to be for the load case that you are thinking about. And your factor of safety is really important to think about, because you can, based on how confident you are in the assumptions that you're making or your design in general, or how well your assumptions in your model represent reality, or even how critical that failure is. Like if your failure is like going to hurt someone, or if you're not sure about your assumptions, then your factor of safety has to be a lot higher. And oftentimes your factor of safety is actually given by industries or companies, but it's really good to think about your analyses and your procedures and how much and how to account for that. Factor of safety is a way to account for your assumptions.
Okay, so last week we looked at the brake pedal example, and we saw there's a lot of system requirements associated with it. There's some constraints and there's some load conditions associated with it. So we're gonna take a deeper dive with it, and we're gonna be following this example for this whole presentation. So as we saw from the rules, is that you need to have a brake pedal that is designed to withstand a force of 2,000 Newton without any failure. So what do we mean by failure in this point? So we really want to make sure that our brake pedal that is able to stop the car in any circumstance, because otherwise that's really dangerous. So we don't want the brake pedal to yield, which means to deform, or nor do we want that to deflect, because that means some of that force that you're applying on the brake pedal is now going into deflection or yielding. So what are we looking for in our analysis? We're looking to see whether that brake pedal is going to yield or deflect greater than 1 millimeter. And I know this might seem really simple and straightforward, but you really want to have a good idea of what you're looking for and what you're trying to get out of your analysis before just jumping into it. So I'm going to talk about a couple types of analysis. This is not a full list, and nor am I going to talk about all the types of analysis here, but we're going to quickly start with the static analysis. So static models just means that they're independent of time. So time is not a factor for the response of your system. So you tend to use a static model when your part's likely to fail in deflection, yielding, or fracturing. And you figure out your loads from understanding your system. In this case, in formula, we tend to know what load we need to meet through our rules requirement. One really important thing that I want to highlight with static modeling is that you can model dynamic model. You can approximate a dynamic load to be independent of time. So that might just mean we're not a system is constantly changing through time and loads are constantly changing, but for the purposes of simplicity, we can tend to model those as static loads. And so the pros of static modeling is that it's really simple, it's insightful, it's quick. With cons that if you need a more higher resolution model to model those dynamic loads, it's not going to provide all that insight. So the next type of modeling I want to talk about is modal models. So this point is if your part is likely to fail in vibration. So what this model is trying to determine, it's trying to determine the natural frequencies of your system. So that means that you want to make sure that whatever frequency your part is vibrating at is not going to be the same as natural frequency. Otherwise, you're going to have resonance. And that just means that you're going to lead to failure. So the pros of model analysis is that it's really simple, it's quick. The cons that it only gives you resonant mode. So if you want to see how your part reacts to other types of vibration, or like just in general response to vibration, you won't be able to see that. It also gives you meaningless deformation numbers. It really just gives you those natural frequencies. So another model we're going to talk about is dynamic modeling. One thing I want to highlight right now is that I don't think anyone's used a dynamic model in the car. They're really complicated. You have to really know what you're putting into this model to get something useful out of it. And it tends to like not even meet, like it tends to be too high resolution for what we need. But some cases of when you're going to be wanting to use a dynamic model is when you have like really explosive events, maybe like head-on collisions that you really have to understand how your system is going to respond in time. Something else is if your failure mode is fatigue, you might need to do some dynamic modeling to understand that cyclic failure. Most of the time, we can probably just use hand calcs to figure this out, but sometimes you're going to want to use dynamic modeling. And then lastly, it's like if you really need to know how your part is going to respond to critical vibrations or some sort of force vibrations, you can see how they respond to multiple vibrations, you might need to use a dynamic model. But again, just want to emphasize, these are really time intensive and they're really difficult to get correctly. Another model we're going to be talking about is topology optimization. So these is really used for lightweighting your pieces. But one of these things that comes with this, one of the restraints that comes along with this is that you really need to know how your system is going to be used really accurately, because it's going to optimize for those loading conditions and those constraints. So if you're not really sure, then you might be optimizing in a way that's not, that might make it fail in a different way. One of the cons is that, another con is that it's going to make you really cool organic shapes, but those are going to be really difficult to machine. So one of the ways you might want to use this tool is to kind of like how the transmission used it for the plates last year I've seen in the images, is that they see where material isn't really needed and then use that to approximate how they're going to lightweight the piece. And then they would do further analysis on that piece. And the last type we're just going to be talking about and really touching briefly on is just thermal modeling. So this is if you want to see your temperature distribution for thermal loads changing in time or not changing in time. And this is really when your failure mode is going to be part failing due to high thermal loads. Okay, so we're going to go back to that brake pedal example that we talked about earlier. So we're going to think about that brake pedal, and we see that we have to withstand these 2,000 newtons. So that's one loading condition. We know that as we're driving, there's going to be vibrations from the car, so maybe we should think about that. And then as well as like we're going to be applying force kind of cyclically throughout time, and so we have to think about how this part will fail. We would use like hand calcs to figure this out, but I'll just tell you right now that that load of 2,000 newtons is going to be the highest, its failure point. The other parts are just not how it's going to fail if you're taking all these conditions.
So assumptions are really important because they are time savers. Because you, in a I guess perfect world where time is not a constraint, you could do many different analyses on every possible load case, but that's just A, not necessary, and B, as I said before, way too time intensive. So you're trying to pick the load case that is most likely to break your part, as Katya was just saying, which you can determine by hand calcs, and just do that or those cases. So the goal, what we've been talking about right now, is you want to create the simplest model you possibly can that still answers the question that you're asking. So a good way of thinking about this is with picture resolution. So Kyle in high def on the left is the original part, right? It is full complex geometry. But it has way too much information and data. You know, if you were to input all the load cases and everything, it would take way too long to run, and you'd be wading through too many results. One layer of abstraction, Kyle in the middle, where you can still tell, you know, it's him leaning on a car, or like a man leaning on a car, is a good layer of abstraction. You keep the important information while having a smaller size and a faster runtime. However, on the farthest right, too much abstraction. You don't have enough loads. Your part is not accurate enough. It's really fast to solve, but you don't get any accurate data.
So like Aurora was saying, you want to abstract your system, and we're not gonna lie, this is like the hardest part of modeling, of performing analysis, because it's really hard to know what assumptions you can make and what you can't make. But like, for example, we're gonna follow along with this brake pedal, and we see the system. So we see, you know, the brake pedal is attached to those two master cylinders, and there's some sort of bias bar that's a press fit into the brake pedal, and as well it's pivoting on that pin joint. But we don't want to input everything because we're going to get too much noise and we might not model everything. So we really want to just focus on the brake pedal. But we need to know how that the rest of the system is going to be affecting it for this analysis. So our first assumption is we're going to make is that we know we have to distribute a load. We know we have a load of 2,000 newtons. So we're going to assume that that load is evenly distributed on that pedal face. And so we're assuming that the pedal isn't twisting, and so there's no torsion. We're making this assumption right now as like this would be like your first case of your analysis, like your first step to analyzing this beam on this pedal, and so we're making that assumption for right now. Another thing we want to think about now is like, how are we going to apply the reaction forces from the master cylinder onto that pedal? So the master cylinders, if you remember, are holding up that pedal, and they're applying two reaction forces, and so we might think, okay, like maybe let's apply that load just directly to that face where that bar is. But we're quickly going to realize that we're modeling our pedal incorrectly, because now we're making it have this huge gap in it. So when in reality, there's a really rigid material right there. So it's not, we're making our pedal weaker than it actually is. So one thing we might want to do is actually have some sort of rigid material in there that we know that is bonded to the pedal. And then we're applying our reaction forces there. And that way we're not actually weakening our material, but we're not adding the added complexity of the bias bar, which is the thing that's pressed into the pedal. So just so you see, we might create like a little fake part that's approximating that, that bar, and we're assuming it's a really, really rigid material, so there's no deflection in that piece. There's some more assumptions we're going to be making, and this is not even an exhaustive list. And I'm not going to talk about them, but you want to make sure, the whole point of this is that you want to make sure that as you're putting something into to be analyzed or to go into FEA, that you really understand what assumptions you are making. So just a quick recap, what we've done so far with this brake pedal example is that we've just determined our most likely failure mode. We've determined what model we should use. And we've determined how to approximate our system. So now let's just clarify what we're trying to figure out. We're trying to figure out if our part will yield or if we're going to see a deflection of greater than 1 millimeter. So this is the exciting part, because we're going to finally see those FEA pretty colors that we're waiting for. Yeah. So here's the results. So we put our things, we put all the abstractions and assumptions we did into our FEA model, and we get these results. What does this mean? So like right now, this is looking at the stress distribution of the part. And it's highlighting from 0 to this random, the max stress of the part. So are we done now? Did we like figure it out? Well, actually we want to like analyze these results a little bit more. So if we look to our left, we're actually, that chart is showing us the range from 0 to the max calculated stress of the part. And on the right, it's actually going from that 0 to that yield stress of aluminum. So that's like, if there's any stress above that yield stress, then we're going to see some sort of yielding. So we're happy to say that no, we don't see yielding in this loading condition. But maybe we're a little bit confused as to why we see this peak stress at this specific point. It doesn't make too much sense. We wouldn't necessarily expect to see stress. And so it's really important to kind of analyze these points. So if you look here, what this is showing you is that stress concentration is actually really close to that split line. And the point of this example is just to show that you want to make sure that you're kind of looking out for what you assume to be correct in your model, or what you would expect to see. And if there's something you're not expecting to see, maybe see how much it penetrates the surface, or if there's something wrong with your SolidWorks model that might explain this. And so if we now go and we look at the deflection of our piece, we see that everything is also less than 1 millimeter. And this is just to show that you can get also different results from your study.
So kind of everything we have been talking about points to the fact that your results are based on the assumptions that you make in the beginning. So your model will rarely get, or it won't get it 100% correct, which is why testing is important, topic for next week. But your model can definitely increase your confidence in your parts because it does better calculations than you can. Thank you, computers. If you are not confident, again, in your model, or again, it has a really high consequence of failure, this should lead to a higher factor of safety. A really important point is when you are presenting any analysis that you have done, either in a design review or even just in documentation on Confluence, please publish all your assumptions really clearly along with the results. This contextualizes your analysis so that when other people are looking at it, they can understand what you're trying to get from your analysis, and also, especially in design reviews, can help you catch mistakes. This is really, like, everyone in industry does this, and this is because, as Katya said before, assumptions are really hard to make correctly. And if you do it in formula, you'll make Colin very happy, like bees, which is exciting.
So going back to that brake pedal example, how do we know if we made it strong enough? So we saw that our, or how do we know what factor of safety we should design for? So the load that we saw that we're designing for is really high. So that 2,000 newtons is the rules requirement. And it is about 450 pounds of port, which is about 3 times the weight of an average person. So already what we're designing our brake pedal to fail under or not fail under is really, really high. And additionally, like, the limited complexity of the model and our design confidence gives us pretty high confidence that if our brake pedal doesn't fail in this analysis, then it will most likely not fail in real life. So we can probably assume a factor of safety closer to 1. That being said, we might want to do some more analysis to see if that loading condition is offset, to see how it does under torsion.
So this presentation, with the past presentations, has talked about how to set up your system requirements, how to then create your part to determine failure through hand calcs, and now has given you kind of an intro to analysis. And so this has set us up for next week when we talk about testing. We realize that this presentation has probably created more questions than it's answered. And that's totally okay, because analysis is really hard. People spend their entire careers just studying analysis. But hopefully this has armed you with the words and like mindset to feel more comfortable doing your own research and also talking to the upperclassmen. Please reach out to us if you have any questions. Reach out to, any other upperclassmen. I'm signing them up for this now. And also the professors at Olin can help out a ton. Yeah. We did not stop for questions during, but if anyone has questions now, feel free to put them in the chat or ask them. Thanks, Naomi.
Thank you, Naomi.
Naomi, just for anyone who didn't say it, is, for reference, 2,000 newtons is about 450 pound force, and is rules mandated that the brake pedal must be able to withstand, which
I covered that later, but it was a good thing to bring up.
We'll wait the
45 seconds.
45 seconds.
No need. I have a question. It seems like FEA has like a very, sorry about the dogs in the background. It has a very set process. So like you find your assumptions and then you determine the test that you want and then you execute the test. And then you compare your results to like your hand calculations for reference. But in your guys' experience, and or anyone else who wants to answer, feel free to answer. Is there any factor or assumption that is easily forgotten when you do FEA?
I don't know if there's like one assumption I can think of, but I know like as you perform, like you might like start with a load case or something, or you might start with your approximations of your system, and you might quickly see that your results aren't exactly what you expect to see, and so you might realize that you missed something, or you constrain your system incorrectly. Another thing I just want to add to that is that this is really sometimes when testing becomes really, really important, because you might realize with your testing that what your analysis is so completely off from what you have actually tested that you might realize you're also missing something critical.
Yeah, a good example of that is actually the chain tensioner from like last year and 2 years ago. We didn't even think to test that if it was going to be excited by the car's movement, right? But it did, and so now we know for future design and analysis to test for that. And so y'all are actually in a pretty sweet position of next year having more testing time to actually be able to start validating those assumptions that are made when you're doing analysis this year and in past years. The other thing is that you're probably, unless you learn how to make assumptions through experience, and that's why design reviews are super important, because when you're expressing your assumptions to other people, they're coming with different backgrounds, and so they can help you think about things you didn't think about, or maybe, and then you can also help them with their assumptions as well. But it's kind of just like the more testing and analysis experience you have, which is, I'm sure, not the answer you're looking for, but it's tricky.
I think another thing with analysis is that they showed you like different types of fixtures, and it's really important how you set up your analysis, because they have like a lot of different options, and each different type of fixture has like different kinds of parameters that kind of govern it, and you can choose how like if it's free to rotate, if it's free to translate. So there's just like a lot of like little details and a lot of like flexibility on how to apply fixtures that kind of reflect your real life situation. So understanding which ones fit your situation best, and like when to choose, like, is this a bound contact? Is this like no penetration? There's just like a lot of like little small details that really kind of add up to really kind of make your total model like good or not. So definitely like there's like a lot of reading to be done. Like even now I still like go through documentation of like ANSYS or SolidWorks to look up like the different options of fixtures that I could use and like what kind of constraints it puts on the piece. And then that's how I decide. But that's definitely something that you should look into, because just changing the fixture or like the way that it is applied really significantly can change what your models, how it performs and what it comes out to be.
One quick thing, I hope you guys didn't mention this earlier, or actually two things. If you when you run your analysis, if you're doing really simple analysis on like a ruler and you want to push on both ends, ANSYS is just gonna like squish that ruler into like a little block. But in real life, if you push on either end of the ruler, it's gonna bend up like out of plane. Like if you take a piece of spaghetti, push on either end, it's gonna bend and break. And that's called buckling. And then ANSYS in like a static analysis won't let something like bend out of plane, because it assumes everything's perfectly in plane, perfectly linear. So that's something to keep in mind. Also, kind of on what Naomi was saying, you've got all these different fixtures and they perform differently, but they can also create false stress risers at your boundary conditions. Because like if you have an immovable object and you put your part here and you push on it, then your immovable object is going to be able to create infinite force, which is not true in real life. Like that's not possible. That's a good assumption to make if you've got one part that's really, really, really stiff and one part that's not. But you have to check that assumption. So it's important to state your boundary conditions and what assumptions are made there, which is kind of said here in the slides before.
Yeah, for sure.